Thank you for your introduction. Good afternoon. So, as was said, my name is Jakub Venclovsky, and I'd like to tell you something about my work regarding fully probabilistic optimization of reinforced concrete elements. To do this, I use heuristic algorithm and neural network. So first, some very brief introduction. There are many mathematical programming applications in civil engineering. You can see some examples here. My work focuses on structural design. As you all know, the structural design, there are two ways to design structures. First is the partial reliability factor method, where all uncertainties are replaced with their characteristic values, which keeps the calculation simple. And there's also fully probabilistic design, which is more complex and time-consuming. Analogically to these two ways of designing, there are two ways of optimization these designs. These are DBSO, deterministic-based structural optimization, which is based on the mentioned partial reliability factor method. It provides optimal solution, but it's quick. And there's also RBSO, reliability-based structural optimization, which is based on probabilistic design. It provides better solution, better in the sense that the random variables are better express the behavior of the structure, but it's complex and time-consuming. So first of all, I will define the DBSO. It's useful because the RBSO can then be defined by only a simple changes from definition of DBSO. So first of all, objective function, which is what's optimized. In this case, for simplicity, it's just cost of materials, but of course, the objective function can be much more complex, usually regarding ecology, some ecology burdens, etc. The design variables, my work focuses on beams. So as you can see, this is an example of beam on which my algorithm can be used. As you can see, it's a 5-meter long beams loaded with normal force and distributed load, and its cross-section is defined by 8 variables, 3 widths, B1, B2, B3, 3 heights, H1, H2, H3, and 2 areas of reinforcing steel, S1 and S3. We will use this example later. The constraints of the optimization, first of all, ULS, ultimate limit state. As you well know, beam has to bear the prescribed load, which is equivalent to strains in concrete and steel, cannot exceed prescribed values. There's minimal allowed strain in concrete for compression and maximal allowed strain in steel for tension is very well known. Then there's serviceability limit states. There are many options what to limit here, but my work focuses only on limitation of deflection. So the deflection cannot exceed the prescribed maximum value. These constraints were very simplified. It was actually just the final comparisons of set values. Of course, the mathematical model itself is much more complex. It uses finite element method to actually assess the ULS and SLS. It leads to the matrix calculation K times U equals F, which is very well known. So much more complex model than it might look like. And now finally to the RBSO definition. It is defined from DBSO, as I said. The differences are that some variables are not random, usually load, material characteristics, and then the constraints are prescribed as probabilistic. Therefore, it's no more its probability of that the constraint will be satisfied is greater than some prescribed number. And what is my proposed method of solution? Since the probabilities have to reach a high level of precision, for ULS, it is depending on the reliability class from 1 minus 10 to minus 4 to 1 minus 10 to minus 6. And it's troublesome to achieve using optimization. So what I propose is to use algorithm, which is divided into inner deterministic optimization, which is based on reduced gradient method, and outer stochastic optimization, which is based on regression analysis. The whole algorithm will be shown on the mentioned example, where the normal force n and distributed load q are random variables with gamma distribution. As you can see, the distributed load around 32.5 kilonewtons per meter, the normal force around 7.5 kilonewtons. So what does the algorithm look like? The calculation is initialized by choosing 12 initialization scenarios. The 12 is a number which was chosen here. It can definitely be some other number of scenarios. The scenario is a concrete pair of values for Q and N. And for these scenarios, when we know the concrete values for Q and N, we can perform the deterministic optimization and acquire the concrete values for design variables and concrete value for objective function. And for these concrete values of design variables, we can assess probabilities that the constraints for ULS and SLS will be satisfied, which is done using neural network. It works in a way that first, some scenarios, some small number of scenarios, usually around 50, are actually computed. And for these scenarios, for concrete values of Q and N, we compute concrete values of strains and deflections, which we can directly compare to the limitation values, as was said before. And on these scenarios, we train the neural network to be able to compute this dependence, and then we send to the neural network a large number of scenarios, usually million or more, and the neural network can assess them very quickly. There are, of course, some errors. There are some control mechanisms in place so that these errors wouldn't happen, but that would be too detailed for this presentation, I guess. So what's next? We have the initialization scenarios, and now we apply regression analysis to them, which approximate behavior of objective function values and probabilities with regards to the values of random variables Q and N. Here are some pictures. So this is a picture of the red crosses are the 12 initialization scenarios, and it's the pair of Q and N and corresponding value of objective function F. To the black cross, I will return later. Here is the same for probability that the ULS constraint will be satisfied, and the same for the SLS constraint. And now the next scenario is selected based on these approximations. So we select scenario which in the approximations satisfied the probability constraints and has minimum objective value. This is the black cross, which can be seen here. So it's the future scenario which will be tried as a possible solution for the problem. The same for ULS, SLS, and their probabilities. And now this scenario is also assessed. First, the deterministic optimization is performed. So we get the values of design variables and the value of objective function. And we can also assess the probabilities, again, using neural network and Monte Carlo simulation. And now, if the probability constraints are satisfied, then these values of design variables are our solution, and the problem and the algorithm can end. And if they are not satisfied, we put this scenario into the set from which we do the regression analysis, and we continue with next iteration. This concrete example took 20 iterations to solve. As you can see on this picture, the red crosses are, it is again for objective function value. The red crosses are the iteration scenarios and the initialization scenarios. The black cross, the only black cross there, is the scenario which will actually be the solution, because it will be found that the probabilities for this scenario satisfy the constraints, and therefore it is the solution and algorithm end. Here is basically the same picture for probability that ULS will be satisfied. You can see some large errors in some points. That's because of the way the probability is assessed. There are some, in some cases, the probability is only estimated because it is sure that it cannot reach the desired value, and therefore it leads to a big error. But it is not a problem, because the regression is weighted. It is weighted in a way that the closer the value is to the desired value, the higher the weight, and therefore large differences doesn't matter. And here is the same for probability that SLS will be satisfied, with the black cross being the final solution. So what are the results? On the first line, you can see the probabilities that were desired as you can see, on the second line are the probabilities that were actually obtained that corresponds to the last selected scenario. As you can see, the probability for ULS is only slightly higher than the desired probability, which is fine. The probability that the SLS will be satisfied is highly larger than the desired probability, which is simply because the ULS was the decisive factor here. There is also the scenario for which the solution was found. I didn't include the solution itself because it was actually, in this concrete example, I allowed the design variables to be different in all. As I mentioned, there are finite elements, and I allowed that in each finite element, the design variables can have different values. So since there are 10 finite elements and 8 design variables, it is overall 80 variables. So I guess it was too much. And that will be all. Thank you for your attention.